So, hello everyone, welcome to tutorial number 10, and I hope you have tried all the problems. There are actually 6 problems, and all of the problems are relatively simpler as this is the first tutorial of this fourth part of this quantum mechanics series. So, it's first part of the, fourth part of this PH101 series. So, this is quantum mechanics. So, in this problem number 1, so let's read it. Planck's formula gives the energy density of the spectral radiance at a given temperature T as this. Okay. Everybody, can anybody confirm if it is visible to you?
Yes,
Yes,
Bhaiya.
bhai, yes.
Okay, good, good. So our energy density function formula is given to us. Okay, this is the Planck's formula. Now we are supposed to derive the Rayleigh-Jeans law from this formula, which is valid in large wavelength regime. Okay. So there was one slight mistypo. So there was one lambda inside here. So if you see hc by kbt, this is here. There is a missing lambda. So let's put this lambda. Okay. So for large wavelength regime, we have to find the energy density. So if lambda is very large, suppose my lambda is greater than hc by kbt, then what will happen is hc by lambda kbt will be very less than 1, right? Everyone agrees?
Yes,
Yes,
Bhaiya.
bhai.
Yeah. Now e to the power x for x very less than 1 becomes 1 plus x for x very less than 1. So we will use this approximation. So let us use this approximation. So this will become lambda to the power 5. Okay. E to the power hc by lambda kbt will become 1 plus hc by lambda kbt, right? Now minus 1, so only this part remains. So this will be lambda kbt by h. So this is the formula. This is the Rayleigh-Jeans law. Energy density lambda t is actually 8 pi kbt by lambda to the power 4. Energy density varies with lambda as lambda to the power minus 4. Everybody got this formula? Did you guys try? Did you guys get this formula?
Yes, Bhaiya.
Yes, bhai.
Very good. Very good. So next part, note the formula at low wavelength limit, namely Wien's law, can also be derived from the Planck formula. Okay, so you try this one at low wavelength limit. If lambda is very less, that is lambda is very less than hc by kbt, then Wien's laws would be derived from this. So Wien's law is actually lambda max into t is actually a constant. This is the Wien's law. Actually, if you plot this function will look like this, and you, because you know this u function, you try to get the maxima of this function du by d lambda equal to 0. You will get the maxima lambda max from here. You will get this point lambda max, and you just get this lambda max and you multiply with t and you will get a constant. Okay, you try this one. Anybody tried, by the way? No one? You try this one. Okay, this is also very simple, just a derivative is away. Okay, next, using relativistic expression, calculate the kinetic energy of proton of wavelength 0.5 Fermi meter. Some voice is breaking, someone's mic.
Yeah, if we are not talking, you better keep the mic mute because we are using the recording now. It will disturb the recording sequence.
Okay, so lambda is given to us 0.5 Fermi meter 10 to the power minus 15 meter. Rest mass of the proton is also given to us 940 MeV. M0 is 940 MeV. and we are also given this Hc is equal to 1240 MeV per meter. Okay, then we can use this 0.5 per meter. Next, calculate the kinetic energy. So before we calculate the kinetic energy, let us get the momentum, because kinetic energy, we know that kinetic energy in relativity can be written as total energy minus rest mass energy. Okay. Now to get this total energy, we will write this expression: E square is equal to P square C square plus M naught square C power 4. And from now to get this E, we need the P. So for P, we will use the de Broglie wavelength formula. P is equal to H by lambda. And we, by the way, need PC. So let's multiply with C, HC by lambda. So you get PC. PC is actually 1240 MeV Fermi meter divided by 0.5 Fermi meter. It means we are having 2480 MeV for PC. Now we substitute here the PC value. This is just substitution now. If you get the points, 2480 square plus 940 whole square MeV square. So therefore your E, if you take the square root of this quantity, it will come out to be equal to 2652 MeV. Now you know E, so finally you will get the kinetic energy. You just substitute it. The kinetic energy will come out to be equal to 1712. Straightforward, right? First, you want the kinetic energy, so let's write the kinetic energy like this. Here you need energy because you know the energy formula in relativistic case is like this. Here you need P, so to get the P, we use de Broglie formula. Any doubt?
No, yeah.
Okay, good. Next, using uncertainty principle to establish why neutrons do and electrons don't reside inside the nucleus. Okay, by the way, what is the uncertainty principle? Delta x into delta p is always greater than equal to h cross by 2, right? Now, the diameter of the nucleus can be taken to be 4 Fermi meter. So, the nucleus diameter is given. This is actually 4 Fermi meter. The rest mass energies of neutrons and electrons are also given to us. So, now let's do it. Why neutrons reside inside but electrons cannot? So suppose because delta this diameter is 4 Fermi meter, the position can be from here to here anywhere. So our delta x can be approximately 4 Fermi meter, and let us do for this the minimum uncertainty case, like delta x into delta p approximately equal to h cross by 2 case. It will be definitely greater than this now, and let us write delta p to be approximately equal to p. So from here you will get P to be approximately equal to H cross by 2 delta X. Okay. Now suppose let us do this for neutron first and assume our neutron is non-relativistic. We are assuming this. Okay. If we finally get that yeah our non-relativistic assumption is correct, then yeah our assumption will be okay. But if something violation will happen after assuming this, we will again go back to the relativistic case. So assuming non-relativistic case, what will be the kinetic energy of these neutrons? It will be simply p square by twice m. This is valid only for non-relativistic case. Okay. Now you know the p. P is actually h cross by p. Okay. P is this much, h cross square by 8 m delta x square. Okay. You are give okay h cross c. H cross c is actually 200 MeV Fermi meter. Okay, you remember these results also. These results will be used If you use these results, the calculations becomes easier. So this will be okay. Let me multiply with c square both sides on top and bottom. So this will become mc square delta x whole square. Now you know the h cross c is equal to 200 MeV per millimeter. MeV Fm whole square divided by 8 mc square m naught c square, you know, 940 for neutrino or for neutrons, 940 MeV, and delta x is given to us to be equal to approximately 4 per millimeter. Okay, so if you simplify this, your value will come out to be equal to uh, around how much? 0.3. Okay, 0.3 MeV. Now see, this 0.3 MeV is very less than our rest mass energy. 940, very less than 940 MeV. That means our assumption was correct. Our kinetic energy is very less than the rest mass energy. That means the particle will exhibit the non-relativistic motion. Okay, are you guys with me?
Yes,
Yes,
sir.
Bhaiya. Yeah, good. So
Yeah,
because yes, tell me.
excuse me. Yeah, I didn't get why did you take delta p equals to p?
We do not know what will be the delta p value. Let us assume that the delta p will be also of the order of p. Now, if you proceed with this same formulation for the electron, then what will happen is your electron kinetic energy, if you assume that this is actually also a non-relativistic case, then it will come out to be equal to 200 by 8 into 0.5 into 4. Okay, and this value will be equal to approximately 12.5, which will be very greater than your rest mass energy of the electron. Okay, that means you cannot directly choose that our electron will be a non-relativistic particle. Okay, so that's why we cannot proceed in this direction. So suppose suppose our electron is a relativistic particle, and suppose the extreme case of it, extreme case of relativistic particle, suppose this velocity is approximately equal to c, assume, let us assume like that, then our energy will be equal to p times of c, and this can be written as h cross c divided by 2 delta x. Okay, so this will be approximately equal to 25 MeV, which is which is very greater than our m naught c square. That means our assumption is correct. So from here, if you find the kinetic energy, then you will get that the kinetic energy is actually 24.5 MeV. That means this is a relativistic particle. And if you find the velocity corresponding to this, it will come out to be equal to, if you write this energy to be equal to gamma, we know na gamma energy is equal to gamma m naught c square. From here you find gamma,
Yes, sir.
from here you find beta, it will approximately go to c. The velocity will approximately go to c. Now that means if your electron is inside the nucleus, if your electron is inside the nucleus, the velocity of the electron should be close to c, which is not that possible. That's why it is outside. Agree? Yes, Surya.
Yes, sir.
Okay, next the Compton effect problem. So what happened in Compton effect is there is a electron.
Sir,
Yes.
the third part, like, can you explain the last part again? How is the relative, like, how do we, from the relative part, get that it is, it can be in the neutron or it can't be, it can be in the nucleus or it can't be?
Because for this neutron, this velocity is very less than c. Okay, so it can, if even if we assume that our position is fixed within this nucleus, then our neutron will be having very less velocity. Okay, it can stay inside. But if
Okay.
but for electron, if you assume that we fix these positions, then the speed of our electrons are approximately equal to c. So that's why we are saying that it cannot be staying inside staying inside this nucleus. It will be actually away. Now,
Okay, sir. Okay.
okay. So if you even assume that the nucleus is small, like this is for 4 Fermi meter, it is given, right? If you suppose that it is inside 1 Fermi meter, then your speed will cross c. In this region, it cannot stay at all because it's impossible. V is greater than C for this region, for 1 fermimeter less than region. But this 4 fermimeter less than region, there is this less sense because V is also approximately close to C. Electrons are having very high speed within this region. So that's why we cannot say that electron will be inside this region. Are you guys with me?
Yes,
Yes,
Bhaiya.
भैया, got that.
Okay. Okay, next, Compton scattering experiment. Photons of wavelength this much, suppose lambda 0 wavelength photon is coming and incident on a stationary target. Suppose this is a stationary target, and after this, what happen is the photon scattered at an angle 90 degree. So photon scattered here, and suppose the particle also moves like this with some momentum particle E. Just let me write. Okay, yeah. So this angle is given to us. This angle is 90 degree. And suppose this wavelength is lambda prime. Then from the Compton scattering experiment, we know that lambda prime is actually equal to lambda prime plus h by mass of the mass into mc square 1 minus cos theta. Okay. So now you are given this lambda 0. You know this lambda 0 and 0.248. Our first part is to find the wavelength of the scattered photons. So we want the lambda prime plus. Now the target used to be in the Compton scattering is actually electron. So let us write this mass of electron here. Then I think something I had done. Yeah, this is h by mec. So now this will be 1240 electrovolt nanometer, and we have to multiply with C also, na? Hc by mec square. Cos 90, 0 again. So this will be simply like this. You substitute this. This is in Armstrong. So this will be 0.248 Armstrong plus Hc. Hc we have already found in the previous calculations that it is 1240 MeV per millimeter. Mass of rest mass energy of electron is 0.5 MeV. So you substitute this, it will come out to be 248 Armstrong plus 2 times, it will become 2480 Fermi meter. So let me write it in terms of Armstrong. So this will be this much Armstrong. So this will become 0.272 Armstrong. Everyone agrees? The main part is this formula, right? You have derived this formula, I guess.
Yes, भैया.
Yes, Bhaiya.
Yes. Next, the momentum of the incident and scattered photons. What will be the momentum of the incident photon? P0, it will be h by lambda 0, right? You can find this. It will come out. You will substitute this lambda 0 from here. 0.248, it will come out to be equal to 2.672 into 10 to the power minus 23 kg meter per second. You can also find the final momentum of the incident, final momentum of the photon P prime. It will come out to be equal to h by
भैया
lambda
it is
prime.
किलो
Yes,
भैया it is okay if I find the momentum in kilo electron volt per C, right?
yes, it's fine. 432.433 into 10 to the power minus 23 kg meter per second. Next, third part. What is the momentum of the scattered electrons? So we want this PS vector. How to find? It will be having some this component x cap component. Suppose this is x cap and this is y cap. So x cap component will be the initial momentum of the photon, right? It will be same as this initial momentum of the photon. Because this is going at 90 degree, we can simply do this. It will become P0 x cap plus P, this P prime, this magnitude, y cap magnitude will be same with this. So this why this will be P prime y cap. This part is fine. Third part is fine. Everybody.
Yes, ma'am.
Yes,
Okay,
भैया.
good. So these are just based on this formula. I hope this is very simple for you. Anyone have any doubt? Only 3-4 people used to respond. Okay. Next question number 5. This was actually plus 2 problem, right? This was there in NCRT. Okay, there is a metal which is having some work function 2.76 electrovolt, and upon illuminating with two different wavelengths, namely lambda 1 and lambda 2, find the maximum kinetic energy of the ejected electron. Okay, so first let us find the energy of this lambda 1 and lambda 2. So E1 will be equal to hc by lambda 1. hc, you know, 1240 electrovolt nanometer by 500 nanometer. So it will come out to be equal to 2.48. Also find the second energy of the second wavelength. It will come out to be equal to 1240 divided by 400 electrovolt is equal to 3.1 electrovolt. Now see, this E1 is less than the work function of the metal, but this E2 is greater than the work function of the metal. Will there be any ejection of the electron from this lambda 1?
No,
No, because
it
the
is
material, yeah, because the material is
lambda.
having bigger work function than the energy of the incident electron, incident photons. So in this case, no electrons will be coming out, but in this case, electron will be coming out. So what is the maximum kinetic energy that the electrons can have? This will be,
Energy provided minus work function.
yes, 3.1 minus 2.76 electron. Now see, this value is actually 0.34 electron. Okay. Now this value is very less than our rest mass energy of the electron, right? So this electron will be coming with non-relativistic speed. Anyway, now what are the corresponding de Broglie wavelength? De Broglie wavelength is equal to h by p. But why this step is important? Why I am writing this step? Because to write this p, you have to be very careful. Either it is relativistic or non-relativistic. Okay, if it is non-relativistic, then only you can write your kinetic energy is equal to p square by twice m. Okay, so from here, because we know it's non-relativistic, so that's why I can simply write our p to be equal to 2mk. Okay, now you substitute the kinetic energy directly here. You will get that de Broglie wavelength will come out to be equal to 2.1 nanometer. Everyone agrees? Any doubt?
No way.
So the last problem. The dispersion relation of the gravity waves in an ocean is at a depth d is given. Omega is equal to root over gk 10 hyperbolic kd. So do you guys remember what is 10 hyperbolic x?
E to the power
Yeah,
x
we
minus e
actually
to the power minus
used to
x
get it
divided by
back.
e to the power x plus e to the power minus.
Yes, correct. So it's actually as we have said, e to the power x minus e to the power minus x by e to the power x plus e to the power minus x. It's actually sine hyperbolic x divided by cos hyperbolic x, and sine is having e to the power x minus e to the power minus x by 2, and cos is also e to the power x plus e to the power minus x by 2. Okay. Now, in first part it says that in general at large depth kd is very greater than 1. Okay. With this approximation, find the relationship between phase velocity and groove velocity. What is the formula for phase velocity, by the way?
Omega by k
Omega by k. What about groove velocity?
d omega by dt.
D omega by dk. Now, because our kd is very greater than 1, that means our x is very greater than 1. If your x is very greater than, so our 10 hyperbolic x will become, this part will become approximately equal to 1, sorry, equal to 0. No. Yeah, this will be 0, this will be 0, e to the power x, e to the power x will remain, that will get cancelled, so it will become 1. If your x is very greater than 1, then 10 hyperbolic x is equal to 1. Everyone agrees here?
Yes, Vijay.
Okay. So, in first part, for kd very greater than 1, our omega is actually root over of gk. Okay. So, it's simple now. To get Vp is basically omega by k, so it will become g by k. And Vg will become root g is constant, dd k of root over k, 2 root over k. So this is nothing but 1 by 2 Vp. Simple. So this is the relation between group velocity and phase velocity. Now for the second part. What happens to such relation in 1 when d is not too large? That is close to shore. That means your d is very less than 1, or kd will be very less than 1. In such case, x will be very less than 1. If your x is very less than 1, what will happen is 10 hyperbolic x, you can write it as e to the power twice x minus 1 divided by e to the power twice x plus 1. Because x is very less than 1, you can write 1 plus twice x minus 1, and here 1 plus twice x plus 1. So this twice x, we can write it like this twice x, but here 2 plus 2x, because x is very less than 1, you can approximate it to be equal to 2. So this becomes x. That means for x very less than 1, your 10 hyperbolic x is actually equal to x. You might have done this kind of approximation earlier, right? For 10 hyperbolic x you have not done, that's why I am writing.
Yes, yeah.
Yeah.
For 10x, we have done that like this.
Yes, God.
So now your omega will become root over of gk, okay, gk into kd, gk square d kgd. So vp will become omega by k gd, and vg will become d omega by dk, which will also be gd, which will be equal to Cp. So this is the relation when your d is not that large, and this is the relation when your d is very very high.
Bhaiya, can you please explain the 10H X approximation once again in the second part?
In the second part here,
Yes, sir. Yes, sir. Yes, Bhaiya.
so you have so here what we have done is what I am writing e to the power minus x to the equal to 1 by e to the power x. So now you take LCM e to the power twice x minus 1 ऊपर. So here e to the power twice x minus 1, here e to the power twice x plus 1. Because x is very very less than 1, e to the power 2x can be written as 1 plus x. So here, and 1 and 1 will get cancelled, so here 2x remains, and here 2 plus 2x, because x is very very less than 1, finally again I am writing 2 plus 2x to be equal to 2. Is it fine?
Yes, Bhaiya. Yes. Thank
Okay,
you.
okay, good. So yeah,
You may continue. Yeah.
so that so I was just wanted to say that because this is the first tutorial of this quantum mechanics, these problems are very straightforward for you, and rest of the problems will be little bit tricky, rest of the tutorials will be little bit tricky, and I just request you to attend the classes. This will become very interesting.